Um, so today I'll go through an introduction and some fundamental ideas, and the ideas kind of give a broad framework that actually captures a lot of things that we'll cover in the course. So towards the end of today's lecture, I'll go through and um, go through each lecture that we'll have, and then say how it kind of fits into the framework that I just introduced. And then at the very end, we'll go over kind of all of the fun stuff like the course policies, late days, um, registration, things like that. So we actually have a lot to get through today. So with that, I'll get started. Oh, I also want to mention that we have the course webpage here. So I'll talk about it at the end. But the course webpage is here. So it has readings. There's actually readings for today, but some people might have not seen the webpage, so it's not a big deal. But if you want to go after today's lecture and read more in depth about some of the ideas I introduced, then definitely check this out. We'll also have code examples throughout the course. So there's this code repository here, and it'll basically be added to um, prior to each lecture. So currently it just has the code for the first lecture in there. Okay, so first question is, this course is called Advanced NLP or Natural Language Processing. So what is natural language processing? Well, it's one of these things that doesn't really have a, one single definition. So here's one that I kind of came up with. So it involves technology that enables computers to process, generate, and interact with language. And some key aspects of NLP are that we're often concerned with learning useful or good representations. So we want to capture some sense of meaning that's present in data, in text data, and other types of data, in some way that we can ultimately use for different downstream tasks. So for instance, some embeddings that we can use to classify a document or to answer a user's query or something like that. Most of the techniques nowadays involve a notion of generation, so generating language. So creating language, whether it's text or code. And this could be for various tasks like dialogue. You're probably familiar with, ChatGPT, translation, question answering, a variety of different tasks. And then finally, kind of going beyond maybe traditional NLP, nowadays, a lot of people are thinking about how you combine language with actually taking actions in some environment or in some world. So here you might use language to perform different tasks, to solve different problems or interact with some environment. And so language is just part of this larger environment, and then ultimately you're taking actions to achieve some goal. So we'll talk about that in the course as well. So here's 3 different examples, and this I didn't change from last semester, so these are actually from January. And as you might imagine with this field, these do become outdated, but at the same time, they're also still very relevant. So here was at the time the state-of-the-art model, DeepSeek version 3. And here's the site called together.ai. And this is one of these language model API websites, and they have this interface where you can chat with a language model. And so here I just typed in this message, and it's a bit small, so maybe I'll read it. And it says, "Hello, I'm showing an example of large language models or LLMs to my class. Can you generate some cool looking text that shows off your capabilities? Maybe something brief with English, Japanese, and Python." So kind of creative combination, and it comes up with something. And it generates some Python code. It says, "Language models can bridge cultures and technologies, creating something, something." And then it gives us some Python code called with a function called bridge cultures. And then it prints out the message. So just kind of random, but as I'm sure most people are familiar with nowadays, if you use something like ChatGPT or some type of, generative AI tool, now a lot of people are familiar with stuff like this, but even just, 1, 2, 3 years ago, this kind of thing was like brand new. And so we'll learn about, most of the key ideas behind building a system like this. Here's another example, and this was again really recent in January of this year. So this one's called OpenScholar. And this predated, if you've used these tools like deep research, this kind of predated those. So the idea is you can type in this query. So I asked it to summarize the key contributions of this paper. And then it's going off and it's retrieving various documents and combining information from them. And then it's using a language model to come up with a summary. So I won't read through the whole summary, but this is a paper that I was a part of, so I was able to kind of check it, and it turns out it's a pretty good summary. Um, and so again, here you'll actually have a whole homework on these kind of retrieval augmented generation models that are really one of the key ideas behind systems like this. And then here's one more example. So this is this tool called OpenHands. So this is developed by Graham, who has taught this course multiple times. He's a professor here at CMU. And here we have what is called a software engineering agent. And so on the left here, you can kind of have this conversation with the agent. So I said, I want to learn about matrix multiplication in PyTorch, maybe to review, some basics for this course. Here it searched the web, it got some documentation, probably, and then came up with this message. And then I said, cool, can you make a simple example in a file? And then so over here you have this code editor, and yeah, hopefully pretty soon it'll produce some code here. So here it comes up with this example, and then you can keep going. You could say like, how about an example with different dimensions, because this one's kind of boring. And then I can go and edit the code. So again, in this course, we'll go over agents. We'll go over techniques for training agents based on reinforcement learning, things like that. And so you'll see, some of the key ideas behind this area, which is like one of the active research areas in NLP right now. Okay, and so if we think about uh, starting to formalize things a bit, these different tasks that are performed by NLP systems, they often involve some input and some output. So you have some input X and some output Y, and maybe we could define an NLP task as, X and Y somehow involve language in them at some point. So some examples, your input could be text, your output could be a label. That's typically called classification, text classification. Your output could be text in another language, then you have translation. You could also have non-text inputs, so you could have an image and then output some text. So an example of this is image captioning. And we'll go over, we'll have 2 different lectures on these kind of multimodal models. Or you could have, instead of just looking at, something like translation, you could have a search query, and then your output is not necessarily just some text, it's actually a list of documents. And so that is this information retrieval, which we'll talk about as well. Or your input could be some state of some environment. It might be, in this code agent, it might be the state of the repository and the conversation you've had so far. And then ultimately you want the agent to output some action. And you could frame many different tasks in this way. Okay, so then just at a pretty high level, we could think of what are some different ways of creating these NLP systems. Um, So one way, valid way to do this is to basically go through and write a bunch of rules and try to come up with a system that's useful. So let's say you want to build a classifier and it classifies whether you know, some document is a sports document or some other document. And so what you could do is you could try to write down every single sports related word and then basically do a loop through your document. And if one of those words appears, then you could say it's sports, and otherwise you say it's an other document. Um, or you could do some type of machine learning. So in supervised learning, we would have this kind of paired data. So you'd have your inputs paired with some output label. And now you don't necessarily have to write down all these rules. The hope is that by applying this training algorithm or learning algorithm, you could get some model which can take in some text and then output the class. Um, and then finally, this is becoming more and more common in NLP. So even like last semester, I don't think I had it on this first lecture slide, but it's becoming an important uh, part of developing the state-of-the-art systems, which is reinforcement learning. So here you kind of set up some environment, and then you get some states and take different actions in the environment. And your goal is to maximize some reward function in the environment. And so we're not going to go into detail here. We'll have lectures on this, but you can kind of see how it's a bit different from the supervised learning setting. And then these different settings will have different data requirements. Um, so another way that you could create an NLP system is to do prompting. So for instance, in the input to a language model, you can describe a task and maybe give it a couple examples. And so there you might have very little need for data. You're just kind of describing the task. You could also, as I mentioned, give the model a few examples, and so that increases the amount of data that you need. And then if you actually go to train a model or fine-tune a model, then you kind of have to assemble this training data set, and so the data requirement increases. Um, let's say you want to do reinforcement learning, then you have to construct this environment and kind of frame your task in terms of what are your inputs, what are your states and your actions, and then what is a reward that kind of says whether given actions are good or not. So the basic idea here is whatever strategy you use, you end up having to think about what type of data you do or don't have available to you, what other forms of supervision you might have, and then how you can use that for building your NLP system. Okay, so um, just to motivate a lot of so most of the techniques in this course will be based on machine learning. And it's actually kind of fun to kind of motivate, why do we need machine learning? Why do we need neural networks? Um, and so here we're going to actually build one of these rule-based NLP systems um, to kind of motivate the learning-based ones. So here we are looking at the task of classification. And so we're given some review from some website, and we want to decide whether the review is positive, negative, or neutral. Um, so these might be movie reviews, and so I hate this movie. I guess we'll say it's negative. I love this movie is positive, and I saw this movie is neutral. So if you formalize this a bit, then the goal is to design this classifier, and we'll use G to denote the classifier. It'll take in some input X, which is the input sentence. And then we have these three different labels, -1, which is negative, 0, which is neutral, and 1, which is positive. And so here we're going to assume that we are given some data set of paired examples, X and Y, and we can kind of use that to build the classifier. Um, so a general pattern which will apply to this rule-based one, but it'll actually apply even to, using like a large language model, is to kind of break down uh, the procedure into two different parts. So the first part is computing what's called a feature vector, and this will basically give you some representation of your input sentence. Then you will compute a score, and the score could be basically this weighted sum. So here we have these weights. So this will be a vector, and there'll be h different weights. And then here we have a feature vector, which is 8 of dimension h. And so here again, this feature vector is basically what is the representation of your sentence that's being used to compute the score. And then we'll use this theta to denote the parameters. So here the parameters of the system are W. We have to set these weights when we're doing the weighted sum. Um, and then we'll have the step, and it's called inference, but in kind of natural language, making a decision. And so now once we have our scoring function, we want to actually decide which class this given input X belongs to. And so here we have this inference algorithm or decision function, and it's basically saying, look at the sign. So if the score is positive, we're going to classify it as 1. If it's 0, it'll be neutral. If it's -1, it'll be a negative review. And so actually, in this really simple example, we can kind of see the 3 key ingredients that will appear in almost any method that we talk about in the course. So the first is what I'll call parameterization. So this is saying that you want to build this scoring function, and you have to decide actually how it's kind of implemented. Here we're doing this feature extraction step, and we're assuming that we're like multiplying the features by some weights. And that's something that we had to decide. We had to like design that. And so all of those decisions will kind of go under this umbrella of parameterization. Then once you have your system, you want to actually set the different parameters. So typically we'll use a learning algorithm. In this really simple example, we'll just set them by hand. And then when you actually go to make a decision, this step is called inference. So you've defined your system, you've done the learning, and now you want to actually use it. That step is called inference. So here we have these code examples for the course, and we have this implementation of this classifier, and you can kind of break it into these 3 different parts. So let me actually go through this code here, and let me see if I can make it big enough. So I won't read through everything, but here we're building one of these classifiers. And so here is this feature extractor. This was denoted as f of x in the slides. And so here you could see that what we've done is try to list all of the possible good words and all of the possible bad words. And anytime a good word appears in the document, then you'll increment this feature up by 1. Similarly, anytime a bad word occurs, you'll implement this bad word feature up by 1. So it's basically counting how many good and bad words does the document have. Then we have an additional position, which is called a bias. And this is basically saying like, what is a good default score to put into, what is a good default score for the classifier? And so maybe we set it to something positive. Then here we have to set the weights. And so we can kind of use our intuition and say, well, maybe we can weight the good words as positive and the bad words as negative, and maybe choose 0.5 for the bias because it seems like a good number. And then what you could do is you could actually use the training set and as a human go through and try to, build up the set of rules, expand this list of good words and bad words, and try to build a really good classifier on your own. So now we can read in the data. So this code example, if you want to run it, actually has data. Here's an example movie review, and the label is 1, so it's positive. And then here is our inference function. So here we're basically going through, and this is implementing the weighted sum. So yeah, here we have the feature value and then the feature weight, and it's just kind of this, naive, simple implementation of weighted sum. And then we choose the class based on the score. So now what you can do is you can go over your data, like your development data, or if you're done with development, then your test data. And then you can measure the accuracy of this classifier. And so here it got, this is just the label counts. And then here's the different accuracies. So it gets 43% training accuracy and 42% dev or test accuracy. And then finally, you can do some error analysis. So you can look at examples that were classified incorrectly. And so let's take a look here. The leads we are given here are simply too bland to be interesting. So does anyone know why this was classified as positive?
We thought interesting is a good word and we only focused on that, and bland was, and other negative words were not there in our classifiers.
Yeah, exactly. So it gets hard to kind of capture all the different cases, all the different nuances with this kind of hand specified word list. So yeah, I won't dwell on this too long, but these are the same steps that you'll go through with most NLP systems, and you can often get a lot of insight by actually looking at the outputs and kind of seeing where it goes wrong. So again, to kind of motivate the methods that we'll see after this, some cases that this really struggles with are low frequency words. So, we might have not thought to put the word tenuous in our negative word list, or this other word purport. Yeah, similar like this. So your set of rules basically have to cover the common words, but then also these kind of lower frequency rare words. Also, let's say we come up with a really good word list. Well, then there's kind of like different forms of words. So if we only have entertaining or like entertained, then we have to account for these different forms of the words. Or if we have long, then you could say overlong. And so possibly we can build in some kind of linguistic analysis here, and it kind of makes the system a bit more complicated. Then you could start looking at the structure of text, and so sometimes we have negation. So this one is not nearly as dreadful as expected, and so you kind of have to program in this logic that starts appearing when you have negation. So here you could start to come up with rules. As the inputs get more complicated, you might miss some edge cases. And it actually turns out to be kind of hard to kind of program in all of these nuances that come up with negation. And then here's a tricky one. Let's say you want the system to understand kind of metaphors or analogies. So puts a human face on a land most Westerners are unfamiliar with. And you ultimately want the system to say that's positive. And so here again, it starts to get difficult to imagine, like, how do we kind of program this in a way that it'll work in all different situations. Okay, and then just one more, just to drive the point home. Let's say you do all this work and you actually have a really good set of rules. Well, then maybe you want the system to work in other languages. And so then you might have to redo all the work for every new language. And then this is just for classification, right? So there's a lot of other tasks other than classification. And so in general, it's like nowadays we have things like language models and things like that, but it's actually kind of amazing that this seems really, really difficult. And ultimately we want some really general purpose system where for any given input or any given task, we actually don't have to spend that much effort and we can use the system on the task or on the input. So this kind of motivates techniques that will try to learn the scoring function. Let me actually pause for a second if anyone has any questions so far. Otherwise, I can keep going. Okay, great. So here we want to take advantage of the supervision that we get from a training set and try to use some algorithm which kind of sets things in the classifier automatically. So that'll be the learning algorithm. And so ultimately we'll get some learned feature extractor versus one that we kind of hand code ourselves. And then also we can learn these weights to do the weighted sum at the end. Then given this, we can use our inference algorithm on some test examples. So we can take a test example or a dev example, give it to the inference algorithm. This should also have X as an input. And then it can classify new inputs. So here, we can actually think of a kind of, it'll turn out to be like a very general recipe for doing this. And it all comes down to learning this really good scoring function. So if we think about it, what we want to do is take an input and then for each possible class, say how compatible that class is with the input. So like for this review, is it compatible with the class positive or negative or neutral? And so this could be called a scoring function. And it's also called an energy function. So there's this really cool tutorial from 2006 by Jan LeCun, if you're interested in this perspective. And it turns out you can frame a lot of these different learning tasks using these energy functions. And the energy function is just minus scoring function. So we'll just keep with scoring function. And so the idea is you want to assign higher scores to things that are more compatible and lower scores to things that are less compatible. And so here, if we have a binary classifier, then again, we can do this feature extraction and the weighted sum. And then if you want to view this as one of these scoring functions, then this is kind of a trick here. What it's basically saying is if the label is positive, then you look at the kind of how positive it is. If the label is negative, then the system should be outputting a negative score. So you'll do -1 times that, and that'll give you some score. If you have a multi-class classifier, now we want to have this matrix that we're learning instead of just a vector. So what we'll do is we'll again have features of dimension h, but now we'll have features for each one of k different classes. And when we kind of stack them together, now we have a matrix. Then when you multiply that together with your features, you'll get something which is k by 1. So you'll basically get a score for each different class. So then this has a really nice interpretation. Yeah, basically like every element of this vector that you get is going to be the score of that particular class. And then again, we have these three different things involved in learning the scoring function. So we have to decide what is the form and the different parameters of this function, like what is the neural net architecture and its weights. Then we want to have some learning algorithm. So how do you automatically adjust these parameters using your data? And then how do we actually perform inference? So how do we make decisions after learning? So an example parameterization is what's called the bag of words model. So this will kind of motivate the better architectures that we'll look at in just like 1 or 2 classes from now, based on things like recurrent networks or transformers. But this is a really naive one called bag of words. So what we'll do here is for each word, we'll basically look it up in this vocabulary. So here you list out all of the different words in your training set, and then you will represent this word as the kind of position in the word list. So it'll be a bunch of zeros and a single one. Does anyone know what these types of vectors are called? Yeah, one-hot vectors. Then what we'll do is just simply sum them up. So here we have 4 different words. So our feature vector will have these 4 ones and the rest zeros. And then again, you'll just do this weighted sum. If you're doing the binary classification, it'll just be a vector, and you'll get a single number, which is a score. Okay, and so now you want the score to be positive if it's a positive review and negative if it's a negative review. And so now, you know, now at least we're not writing down this list of like good words and bad words. It's a bit more general. It's just looking up kind of word identities, adding them together. So can anyone think of maybe one problem that this would solve that the rule-based one had? Mhm.
It can solve the issue of negation because it can track the negative words as well.
So yeah, you can get around some of the problems because yeah, you can do this weighted sum and some of them will have the negation. A downside of this is since we're just doing a sum, the word order gets lost. So some of the more kind of complex cases of negation will still need something better. Okay. So we'll go into this a bit more in the next lecture. But here's some actual parameters just to make sure this is all clear. So here again with binary classification, we just have this vector of weights. And then with multi-class classification, we have this matrix. And so here, for instance, after learning this word love has a high weight and hate has a low weight. And then on the right-hand side, you could see one way to look at it is like, okay, for a given word, look at the row. So for the word love, very positive is high, and then very negative is negative, and then it's kind of switched for hate. So yeah, ideally you can kind of get this learned matrix, and then it could even have this kind of interpretable form. And the question is, this is a lot of numbers. How do you set those automatically? And that will be where the learning algorithm comes in. But first, let me just talk about inference. So, here, what we want to do with these different models is we often want to find what is the highest scoring class for a given input. So this will be called optimization, maximization, map inference. We'll go into this in a whole lecture about language models. And so here we get our scalar from the bag of words model, and we want to choose the class that's the highest. And to actually write it with notation is like, you kind of have to do this trick with the multiplication. But, it basically comes down to looking at the sign. Like if your model is giving something negative, then you'll choose to classify it as negative, and if it gives something positive, you'll choose to classify it as positive. So nothing crazy here. And then for the learning algorithm, what we want to do is, given this training set, split it into 3 different parts. So a training set, a dev set, and a test set. This is the kind of standard idea in machine learning. So hopefully you've seen that before. I think I will have one slide kind of justifying this in either the second lecture or the third lecture. But anyways, you split your data up like this, and then you want to define some loss function. And here the loss function is going over each individual input and output example. And then you want to run some algorithm that minimizes this loss function. Okay. So we'll talk about a variety of algorithms in this class, just because this is the first lecture and this is like one just kind of quick overview. Here's an algorithm that we, after today, probably won't use, but it's a simple one. I mean, it's an algorithm called structured perceptron. And so here the idea is kind of intuitive. So what we do is we extract features, and then we actually perform a classification. So, take in a document and actually run our classifier. And then we want to update the weights if the prediction is incorrect. So let's say our classifier predicts positive when the data says that we should predict negative. Then you basically use this update rule right here. So let's see. So if the data said that it's negative, then this y will be -1. And so basically you can see that it is decreasing the value of this weight. So kind of intuitive idea. You could spend a lot of time going into the details of this and what it can do and can't do. I won't do that in this course. But here I just want to give this, simple algorithm to kind of complete the story. And again, we have an implementation of this in the code repository. So here you can go and run this code, and you can actually train it, and you can see the training's pretty fast. You might have missed it. Nice, yeah, much faster than the large language models. And now we can evaluate it, and the results are kind of, yeah, they can be kind of interesting. So one thing is we get much higher accuracy training accuracy than with the rule-based model that we had. So now we get about 80% instead of 40. We also get higher dev and test accuracy, which is 58%. Does anyone know why there might be a gap between these two things?
Has data that you didn't train on, so it's like unknown data, whereas train is what it's actually like training on. So it's gonna know the thing it's training on better than like this random other, not random, but like this kept apart bit of data that you're testing.
Yeah, exactly. So when you run this learning algorithm, especially if you run it for a while, then it will be capturing the patterns in the training data, and it could actually learn things that kind of overfit to the training data and don't generalize to the dev and the test data. So we'll see that idea, come up in the course. And then here the error analysis is, I don't know, I think it's more fun than the previous one. So now what you can do is you can look at the incorrect outputs, and then you can also look at the weights that the system has learned and try to get some insight into what's happening. So this one, the true label was neutral and it predicted negative. And you can see it learned that comma is actually pretty positive. This is actually kind of, yeah, so A is 0. Period is negative, and little is very negative actually. So you can see it's kind of, some things are reasonable, enjoyable is very positive, but you can kind of imagine that, when a lot of these things are kind of off, then the system's classifications has these, a lot of these weird kind of weak points. Okay, and then the other thing you can do is you can look at like what are the most positive or what are the most negative weights. And again, it's clearly learning something. So kind of cool with such a simple learning algorithm, it is learning to assign a pretty high weight to, fairly positive things. At the same time, you can find counterexamples pretty quickly. Let me see the negatives. Okay, so yeah, stupid, yeah, pretty negative. TV is negative though. So anyways, yeah, this is pretty cool. But there's still a lot missing in this, right? So we still haven't dealt with this idea of conjugation or compound words. We'll actually talk about that next lecture. And we don't really have a notion of similarity. So it's still just looking up these words in the dictionary. It's never saying like, if two words are similar, they should have similar representations. And then again, as we mentioned, as I mentioned in the answer to the question earlier, this doesn't really capture the sentence structure because we're just summing everything together. And so we'll need to account for these things somehow. And so broadly, the approach is to use neural networks in deep learning. So here, now we start with some vector representation of each word. And then we pass it through this function, which is going to be learned from data. And it's like this complicated function that ultimately produces some feature vector. So now instead of kind of hand designing the feature vector with these different rules or with just these like word identities, now the hope is that this neural network can actually learn a really good feature vector. And then again, at the end, we have the same thing where we do some weighted sum and get a score. So the big question is, this is kind of magical. And so we have to actually figure out a lot of stuff. We have to figure out how do you design this neural network? Like what is a good architecture for different types of data? So that's the parameterization. We have to figure out how do you actually learn this kind of magical function that gives you a good feature vector. Which algorithm do you use? What are the different assumptions for the data that you need? Things like that. And so a variety of questions still, need to be answered to build this system. And then I just want to comment that we've been talking about classification. So this kind of very simple task. But it turns out that this perspective of just learning this function that is really good at scoring things actually is pretty general. So it's a kind of cool idea. And again, it's from this perspective of building these kind of scoring functions or energy functions. So this is just repeating what I said. So you could imagine for classification, as I mentioned, you want the model or the system to assign high scores to correct classes and low scores to incorrect classes. But you can also design a ranking system for like retrieval. So if you're able to, given a query, assign scores to documents in such a way that they're in the correct order, then kind of all you need is this really good scoring function. And then similarly, let's say you want to build this probabilistic model. So like large language models are probabilistic models. Well, then when you think about it, the probabilities are kind of like scores. It's saying, given some input X, so conditioning on some input X, what is the probability of a particular Y? And so again, if we can just learn a really good scoring function, then we could probably turn it into a probability distribution. And if we're able to do that, then you could frame a lot of different tasks in this way, like given some English sentence, what is the most probable Japanese sentence? Given some conversation history, what's the most probable response? And so on. So let me just say a bit more about this, because the idea is really simple. So here we have our scoring function, S theta of X and Y. And then here, what it's basically doing is turning it into a probability distribution. So you have to on the so you have this exponential, and in the numerator you have the score, and then in the denominator you have what's called the normalization term or partition function. And so this is summing up all the different scores, and this ensures that things are each score is between 0 and 1. Each probability is between 0 and 1, and that collectively they add up to 1. So you can get a probability distribution. Does anyone know what this thing on the right is called? Yeah, softmax. So we'll talk about this some more, and if you haven't seen it before, then yeah, we'll talk about it some more. But now you have a system which kind of had these scores which could be scaled in any different way. Like we saw that one of the words had a score of 15, another one is like -2. Now with probabilities, everything's between 0 and 1, and everything sums to 1. So it's kind of nice in that sense. But then you can also kind of build general algorithms for sampling from a probability distribution. So if we can, like if you have a coin, then you can kind of flip it and see if it heads or tails comes up. That's drawing a sample from the distribution that the coin has. And so if we can come up with some way of sampling from these learned distributions, then again, this could be pretty general. So the way to see this is, here, imagine that X is basically anything you want. So it could be text, it could be an image, like represented as in some way. It could be the state of an environment. And then similarly, imagine that Y is anything that you want. So it could be, ChatGPT's response to you. It could be the next action that your kind of agent is taking. It could be an image that you want the system to generate. And so here we can maybe build a more interesting classifier that also kind of gives us a reason. So I hate this movie, and it outputs because it isn't creative or something. Or yeah, this is a kind of contrived example. But anyways, the idea is that you can frame a lot of different things in this kind of probabilistic formulation. And so if we can successfully learn models like this, then we potentially have something that's pretty general. And so an example of this is going to be the large language models. Ultimately, they are a probabilistic model like this, and you can give them inputs and you can sample different outputs. So again, if you haven't seen this before, or if the language that I'm using in terms of like probabilities and stuff isn't familiar, we'll go over this in the next few lectures. Okay. So this is good. And then, of course, if you have one of these probabilistic models, you can also use it to kind of take actions. So typically when we think about a model that gets some state of an environment and takes an action, we call it a policy. And again, you could just represent the input to your model as being the state, and then it could give you this distribution over next possible actions. So let's say that the system was like looking at some movie streaming website, and then the user said, I hate this movie. And then maybe the agent then clicks the pause button or something. I don't know. So this will be the kind of key idea behind these AI agents that are using techniques from NLP, like language models, to take different actions. And yeah, here's some cool pictures. Okay, any questions on this? Next, I'll just kind of go to an overview of how the course is structured and then the logistics. Okay, cool. So yeah, broadly, the reason I introduced this is first because I think it's a kind of interesting general way of looking at things, and it helps you break down the different parts of a learning-based system into these kind of high-level categories. So we can now think about what we're going to cover in the course. We're going to cover different architectures. So these give us good parameterizations, ones that are really general. We're going to talk about different ways to build the probability models. So you could have an autoregressive model. We're also going to talk about diffusion models, which is a different approach. And then we're going to talk about how you incorporate things like images, things like retrieved documents, and things called tools. So if you have some like functionality outside of the learned system and you want the system to take advantage of it. Then we're going to talk about a variety of ways of learning. So learning from unstructured data, kind of data just from the internet, paired data, and then learning if you have some environment with a reward function. So that'll be reinforcement learning. Then we'll talk about inference. So how do you actually do this with, I mean, we'll mostly focus on large language model inference. So optimization and sampling, some more recent kind of multi-sample strategies, and how you get the models to run very efficiently. So like how you get a language model to run on your laptop. We'll see some of the key ideas behind that. And so broadly, the way the lectures are structured is the first half of the course goes over kind of fundamentals. So these are things that, you know, as you're going throughout your research career or whether you're building applications with NLP, are really good to know. And the kind of underlying ideas are the foundation for a lot of other things. And then the second half of the course will have more advanced topics. So this might relate to more recent research areas, or it'll kind of build off of one of the earlier lectures and we'll go into some more depth. So roughly speaking, that's how it's structured. And then there's a few different themes. So in the first few lectures, we'll go over different fundamentals. So we'll do a pretty quick review of deep learning basics and language modeling. And then pretty soon we will get to, pretty soon we'll get to, you know, methods and architectures that are being used in the state-of-the-art systems. So like by lecture 5, we'll talk about transformers and attention. And then this is the topic of architectures. Here's an example of the advanced. So towards the end of the course, we'll talk about these models for very long sequences or these mixture of experts models. Then we'll have a variety of different lectures about learning and inference. So things like pre-training, fine-tuning, and different decoding or inference strategies. We'll also cover these various model types that I mentioned. So like retrieval models, incorporating retrieval models with language models, multimodal, and then at the very end of the course, talk about these diffusion models for text, which is a kind of active research area. And then finally, we'll have a couple lectures which will kind of give you some additional, evaluation techniques. Sorry, we'll cover evaluation techniques and then give you some additional things related to experimental design and kind of basic research skills. So this lecture 14 could be helpful for the project in kind of conducting the literature review and things like that. And running, solid experiments. And then, as I mentioned, there'll be a few different lectures on this RL and agents. And then how do you make the systems kind of scalable or efficient for real world use? So yeah, this course is called Advanced NLP, and over the years, it's kind of evolved based on the current state of NLP. And so the idea here is we're trying to give you an introduction to the various areas involved in advanced NLP. In practice, I'll focus a lot on language models because those are very prominent in today's NLP. But the course is not just about language models. We do have a whole course here about language models. We'll also cover some other things like the stuff I've mentioned. Like we'll have a whole lecture on reinforcement learning that does, but also could not apply to just language models. But for any one of these different areas, we're really lucky here at CMU that we have this amazing set of courses. So you can also go into more depth in a particular area. So here I've listed some different courses that will kind of intersect with a couple lectures in this course. Okay, so now the class format and structure. So again, we're going to learn in detail about building NLP systems, and it'll be from a research perspective. I'll go over I'll try to incorporate things from recent research, and then throughout the course, you'll, especially in the second half of the course, you'll actually do a kind of mini research project yourself for the project. And yeah, we'll learn basic and advanced topics and see several case studies. So before class, please take a look at the course website. So on the course website, we will have these different, so we have the schedule here. And the schedule here will have main readings and additional references. So sometimes the additional references is pretty long. It just means that somewhere in the lecture I mentioned the paper. It doesn't necessarily mean you should go read everything, but it's kind of like, yeah, if you see something in the lecture and want to see the citation for it and want to read more, then that's what the additional references are. The main readings will be a kind of key paper that I think has important ideas for the lecture or provides additional background. Then typically I'll try to pause and ask questions and have discussion questions during class. This one I had a lot of stuff to get through. I wasn't sure if I'd get through all of it. But I'll try my best to kind of stop, see if there's any confusion, things like that. And typically students will ask really good questions and it'll clarify things and kind of everyone benefits. And so also just feel free to raise your hand and I'll pause. And there's kind of time built in to do interactive question answering discussion. And then as you saw, sometimes there'll be a code example, and then it'll be posted to the code repository. And then after class, we'll have a quiz, which is about the class or the reading material. So I think I have a whole slide on the quiz logistics in a bit, but this is just the broad format. Then for the assignments, we'll have 4 different assignments. And so the first 2 are kind of, homework assignments. The next 2 are about the project. So first you'll go through and, with some starter code given, build one of these llama language models, and train it. It'll be a small one that you can train for a specific task, and you'll kind of see the details of the architecture and things like that. And then in the second one, it'll be more of a kind of what are the big parts involved in an actual real world NLP application. So you'll have to do data collection, you'll have to build a model, and you'll have to evaluate it and kind of justify the evaluation, things like that. And so we'll release the details closer to the time of the assignment. And then the next 2 are focused on the project. So broadly speaking, you could think of the project as being a kind of mini research project, maybe mini just due to the enforced time limit of 1 semester. Sometimes research projects take longer. But really you can kind of use this as an opportunity to, try to do something that interests you, try to do something new. Sometimes the course projects end up turning into papers, things like that. Sometimes they don't, and that's perfectly fine. But here we want to basically group together this assignment 3 and 4. So assignment 3 you could think of as doing a literature survey about the topic of your project. So here you want to go out and kind of find out what's been done in this area, categorize it into different parts. We'll give some guidance on how to put together a literature survey, but this is a typical step that's done while you're doing research. Then you'll reproduce results from some paper from some baseline model. And so this will basically serve, hopefully, as some baseline for your final project. So again, usually a step in these projects is, looking at what exists, and then in the task or in the area that you care about, you want to compare your new method with some old method. And you have to be able to, run the result and reproduce it and get some number. And then for your final project, you will try to do something which improves upon the method, or takes some method or some idea and applies it to some new and unique task. And so again, we'll give more kind of guidance about or some details on what this would and wouldn't involve. And then throughout the course, you're encouraged to come to office hours, things like that, post on Piazza to figure out a good project idea. And then at the end of the course, you'll present a poster and write up a report. Okay, so as you can imagine, you can look around, it's kind of a big course. And so everyone has various different unexpected circumstances that come up. And so in order to scale to a large number of people, instead of analyzing any particular situation, what we do is just give you the set of late days to kind of cover different things that come up. So for assignments 1 through 3, we give you a total of 5 late days. where you can turn in the assignment, a day late. That'll be one of your 5, and you won't get a penalty for it. Assignment 4, unfortunately, it's right at the end of the semester, and we have to get the grades in by a certain time. So we can't have any extensions for assignment 4. The quizzes are released by the end of the day of a lecture, so by 11:59. So there's no quiz for today. It'll start on Thursday. And then the quiz will be due at the end of the following day. And so here the idea is to kind of see if you have some understanding of the content, and it'll be based on the content of the lecture and then potentially of the reading. So just to make sure it's clear, for example, next Thursday, the quiz will be released by 11:59, and then it'll be due by 11:59 the following day, and it'll be released on the quizzes are done through Canvas. And then again, to account for various situations that may come up, we will also drop your 3 lowest quiz grades. So if you have to miss a quiz or something like that, then we'll drop 3 of them. So we'll do our best to send a Zoom recording by the end of the day of the lecture. However, we don't make any guarantees, and sometimes various errors come up or it gets delayed. So really the only way to guarantee that you've seen the content for the quiz is to come in person, but we will try our best to send a Zoom recording as well as a Zoom link. Again, because in such a big class, there's so many different cases that come up, so we do try to make that option available. Unfortunately, we do not allow registering for the course if you have a schedule conflict. We do really encourage you to attend the course and participate in the discussions. And then additionally, you absolutely must attend these courses. So when you're deciding whether to take the course or not, please look through your calendar and make sure you can attend these, because they're directly related to the course project. And so these are very important to attend if you want to get a grade for the course project. So please do look through your calendars and make sure you can attend these, because unfortunately we can't make exceptions. We also have a very long wait list, and so it's really great to see all the excitement for the course. So out of fairness, due to the size of the wait list, and because there's so many different cases and everyone has a pretty good reason, we can't prioritize any individual case. So there's basically a way that the waitlist is automatically prioritized, and then I don't make any changes to that. So unfortunately, if you email me, I unfortunately can't make any changes to that. So then again, should I take this course? I might be biased, but the content is going to be exciting. It's going to be a great course. You get a chance to do your own project. But please be sure that you'll be able to deal with the kind of logistics, like take the quizzes, the attendance aspects I talked about for the final project and things like that. And just make sure, because you don't want to kind of run into an issue later where you're not able to make it to the project hours. Okay, and then the teaching team. So I'm Sean Welleck. And we have 8 different TAs. So I don't know, are any of the TAs here? Yeah. One, do you want to introduce yourself?
Joel. I'm a PhD student in LPI.
Okay, great. And so everyone will have office hours. So all have office hours, each TA will have office hours. We will begin the office hours next week. Monday is a holiday, so they'll begin on Tuesday. And all of the office hours will be posted on the course website by the end of this week. So we're still reserving rooms and things like that. But we'll have it all set up, and then if you want, you can start coming next Tuesday. Again, the website is very important for staying up to date. Please do sign up for the Piazza if you're in the course. Also very important for communicating things about the course, homeworks, etc. And with that, that is everything I wanted to cover today. So thank you.